Okay. So let's begin then. Essentially, in the first one, it says state the Newton's law of gravitation for 2 marks. I'm just gonna segregate into 2 parts. So you're gonna say the force of attraction is proportional to the product of masses and inversely proportional to the separation between their centers. So this is what you are doing. Generally, what you want to do is that you guys want to write this. Like you don't have to write this, but it's important that if it's 2 marks, you should actually know the correct law because every part carries a mark. Anyway. Now, going to the next, we are basically, let's see, the planet may be considered as a uniform sphere. The satellite is in circular orbit of period t around the planet at a height h above the surface. And then the height of the orbit can be adjusted by use of satellites' rocket engines. Shows the variation of height of t2 by 3. Interesting. This is something new actually. Okay, never mind. So in this scenario then, okay, so then let's look at this by reference to forces, explain why the orbit satellite is circular. So basically, obviously there's going to be a gravitational force. So there's a object and then there's another object. So the force is the gravitational force, which is providing it centripetal force. That is why it is moving in a circle. So that's why I think you should write that the gravitational force acts towards the, I think it's towards the planet that provides centripetal force to move in a circular orbit. So this is the prime concept that you should always remember. And it will always be asked in these questions. The other thing that you guys need to remember is that when you say acts towards the planet, I think you should also include that the gravitational force acts 90 degrees to the direction of motion towards the planet. This would actually work better because writing this basically helps us understand that the direction of motion of the satellite is like it's not a stationary object, and the force is somewhat like that. So that's important. The next thing we're going to do is the use of gravitational law, and in this one it says that H and T are related by this equation, where G is the gravitational constant, A, B are constant that depend on the properties of the planet. Okay. So show that H and T are related by. So that's fine. So we have on the y-axis T 2 by 3, and on the x-axis is H. And we're going to find this. So I think we're going to take the same path. Gravitational force is equal to centripetal force, the one they asked us earlier. And with that said, gravitational force will be Gmm over r square. This is going to be mv square over r. Now the problem with this is that there are certain quantities that we need to get rid of. Like you see, it says G is gravitation, A, B are constant that depends on property of planet. So I don't think so. We need time period, so we'll have to use mr omega square then, where we know omega square, omega is 2 pi by t. So I guess then m and m will cancel out. There's no m actually, which is interesting. Okay, never mind. Let's try this. This is going to be, I'm going to take r on that side. So it's going to be r cubed times omega square. And then let's put in the omega square value. So 2 pi by t whole square. Oh well. So Gm equals to r cubed times 4 pi square over t square. So this is something that's going to happen, right? Hmm. Okay. Now we're getting something somewhere actually, because the thing is, I can actually get to the point where you see if I take t on that side, so it will be gm times t square over 4 pi square. So we're getting somewhere here. And the other thing that is remaining on that side is just r cubed, which makes sense as well. Now I'll tell you why. Basically, this h needs to be studied. It says the satellite is a circular orbit time period with the planet at a height h above the surface. So h is the height above the surface. So this is h. That means the radius of the planet should be r, and that radius they must be saying it's b. Otherwise, that doesn't make sense, So we can write h plus b cube here, and then if you see closely, we also have M. M has to be A then, because they haven't said anything about that. It's just planet properties. So G, we can then write G A times T square over 4 pi square, hence shown. Pretty difficult, huh? Now it says use the gradient and y-intercept, determine the values A and B, and give the units. So that's pretty easy. Actually, on this side, as you can see, it's T 2 by 3 and H. So if we take cube root on both sides, sorry, let's write the equation again. Ga over 4 pi square times T square equals to H plus B cube. Now, if I take cube root on both sides, then what happens is this becomes H plus B equals to cube root of Ga over 4 pi square times t. Cube root means power of 1 by 3, so it will be 2 by 3. And then h can be written as Ga over 4 pi square times t 2 by 3 minus p. So if I compare this, y equals to mx plus c. So you guys can see h is y, on the y-axis from on the graph as well. Oh, wait, that's bad. H is x. We have to rearrange again. Sorry about that. Not correct calculation. We have to actually. Hmm, hmm, hmm. We have to actually make t the subject, and if I make t the subject, c2 by 3, because this is on y-axis, then this is cube root. So this is going to be, I guess, h over cube root of ga over 4 pi square plus b over cube root of ga over 4 pi square. Interesting. Interesting. Yeah. So then if I compare this with y equals to mx plus c, so I guess the gradient of this graph will be 1 over under root, 1 over cube root ga over 4 pi square, and the y-intercept c is going to be b over cube root ga over 4 pi square. Right? Pretty awesome. One moment. Just a moment, please. Okay, so now my buds, we are going to basically go forward and check what we can do. So to find the gradient, the easiest way that I have always found is that I can basically, I have to go through this point. Let's take the first point and always take the last point. It is the easiest in my opinion, and it's always the standard what the examiners always do. So you can actually do this like that. All right. So now, Alisa, hi. We're doing this paper, okay? So please take it out, and at the end I'll tell you what where to get it from. So then what you gotta do? Let's read it out. If this is 200, then that would be 240 to 280, 320, 360. And so first point is 0 and 360. In fact, okay, and the other point is 12 into 10 raised to the power 6. And this is going to be 1240, 1280. That would be our gradient. Let's take these points to the other point here. That's bad. Okay. So then what you're going to do is that we are going to find the gradient. Gradient will be 1280 minus 360 divided by 12 into 10 is to 6 minus 0. So let's quickly do this. Where is it? Where is it? Where is it? Okay. So 1280 minus 360 and then 12 into 10 raised to power 6. So the gradient I'm getting is about 7.67 into 10 raised to minus 5. Okay, so then what you got to do is we have to find the gradient. We have to find actually A. So to find A, we have the gradient, and it is 7.67 into 10 raised to minus 5 equals to 1 over cube root of GA over 4 pi square, right? So to remove cube root, you can cube on both sides, like cube here and cube the whole thing. So this will become 7.67 into 10 raised to minus 5 cube equals to 4 pi square over GA. Now, again, A is going to be 4 pi square over 6.67 into 10 raised to minus 11, that is G, multiplied by 7.67 into 10 raised to minus 5 cube. Now, here, my buddies, just really quickly, because that's a lot of time we have spent already in this question. So pi squared divided by 6.67 into 10 raised to power negative 11 multiplied by 7.67 multiplied by 10 raised to power minus 5 and cube. So the answer I'm getting for A is 1.31 into 10 raised to power 24, which does make sense because actually that is somewhat like general Earth-like planets mass. So this will be in kilograms. And then we have to find the other thing, which is B. And as you guys can see, B is equal to the y-intercept multiplied by 3GA over 4 pi square, like that. Which is actually like 1 upon gradient. Huh? The gradient was this, 1 upon this. So, yeah. So that means this will be y-intercept multiplied by 1 upon gradient, because we don't have to find it again. Now, let's see if y-intercept, what is that? It's starting from 0, so y-intercept is obviously 360. So I'm going to put it there. And then the gradient we found was 1.67 into 10 raised to minus 5. So let's do this. 360 into 6 into 10 raised to power minus 5. Oh my goodness. Oh my goodness. Well, that doesn't make sense, or it's 1 upon gradient. Sorry about that. Made a mistake. Let's fix it. 1 divided by, put brackets. So this is going to be 4.7 into 10 raised to power 6, which is approximately the radius. So that should be in meters, by the way. So this question is pretty long and difficult. For 5 marks. It's a big question, actually. So yeah, seems like the new papers are not that easy, but let's go to the next part. If you have any questions, do let me know, okay? Now, going to the next, which is define specific heat capacity. Again, for 2 marks, you have to be very particular. I'm going to give you in 2 parts. First, you're going to say it is the heat energy required per unit mass. Now, writing per unit mass is essential because specific means that you are looking at the mass. Okay. And then for the second point, you're going to say in to change per unit mass to change the temperature of substance by 1 degree Celsius or 1 Kelvin. So both are okay, whatever you want to write, that's good enough. Then go to the next and see the 2 solids X and Y are made from different metals. The blocks have different initial temperatures. Block Y is initially at room temperature. Got it. The blocks are placed in direct thermal contact with each other. Shows the variation of T of the 2 blocks. Okay. So one block X is like losing heat, the other one is gaining heat, and they come at an equilibrium temperature, which is right here. So then we're going to check what this is. This is in minutes. Always check that before you start the question. It's very important. So three conclusions that may be drawn from figure 3.1, and this may be qualitative or quantitative. First of all, if I had to write, obviously I've seen that X is losing temperature, right? And Y is gaining temperature. But how much temperature is lost? I think we can do that as well. Okay. So for example, if you see X started from a point which is, I think if this is 75, 50, this is going to be 60, 70, 80, 90. No, that's not going to work. Okay, so this is going to be, let's quickly do this. I don't know what this will be. 100 minus 75. And then we have 20 boxes. So each one is 1.25. Okay, so 1.25, 1, 2, 3, 4. So 5. All right, so this is going to be, I think, this is 80. If this is 80, every 4 boxes is, this is 85, then it doesn't work like that as well. One moment. Why did it go wrong? 25 divided by, oh, okay. I made a mistake here. So 100 minus 75 divided by 10. So each box is 2.5 actually. 2.5 times 4, 10. So 4 boxes are 10. So that means this is going to be 85. And 1, 2, 3, 4. This is going to be 95 and then 100. Okay. So X goes from 85 up till this particular point. So we're going to check what is this. Uh-oh. Let's see this point, right? So this is basically 20, 30, 35, and 40. So this is going to be 40. And X goes from 85 to 40. So we're going to write here, X loses energy and temperature decreases by, temperature decreases from 85 to, what is that, 40, right? Then I'm going to say Y, and in fact, I'll just write it in the same one. Y goes from 25 to 40. So Y gains energy and temperature rises from 25 to 40. So I'm going to write that. All right. Then in the next one, they both reach an equilibrium temperature at 40. So, and that happens around, I think, 2.5 minutes, right? So I'm going to say about 2.5 minutes, both X and Y reach equilibrium at 40 degrees Celsius temperature. All right. The next thing, if you see that within the same amount of time, X, which is at a higher temperature, is losing heat. Like it goes from, in 2.5, it lost like 85, 45 degrees change in temperature, right? And within the same time, Y has only lost about 15 degrees Celsius temperature. So that basically indicates that Y is basically of a larger thermal capacity because it's providing the same amount of energy, gaining more, like the same amount of energy that X is losing, but for a smaller change in temperature. And you can actually see it with the formula as well, because you know heat capacity is given by Q over M delta theta. The one that shows smaller change in temperature has a larger thermal capacity. So you can always look at the formula if you're unsure about anything. So this is what I'm going to write here. I'm going to say Y has larger thermal capacity compared to X. As for same amount of time, rise in temperature is small. So if I were you in the exam, I would actually write something like that. Okay. Then it says the mass of block Y is equal to 1.3 times the mass of block X. The metal in block Y has a specific heat capacity, and metal determine the specific heat capacity of this. Pretty simple. Don't worry about it. First of all, we're going to check what's going to happen. The main idea behind the question, right? So X loses heat, and this heat goes into Y that gains heat. I'm going to simple use MC delta theta in both of these, where mass of X, let's say mass of X is basically, let's call that M, and the heat capacity of X is, let's call this Cx. And then the change in temperature we found for X was around 45 degrees. I think so. Yeah, 45 equals to the mass of Y is 1.3 times mass of X. So we're going to write 1.3 M. Heat capacity is 901. And the change in temperature was only 15. So if you've already done your homework from the previous parts, I think that would help you a lot. And now let's just find it out. M and M is going to cancel out. So ultimately, the only thing that is remaining now is 1.3 times 901 multiplied by 15 divided by 45, which is 390. So I'm going to write 390. Okay, pretty good. Right, my kids? So, by the way, just want to add a tip here so you guys don't forget, don't waste time actually. You see, I took the temperatures in degrees Celsius, although the answer is required in Kelvin. So, remember, change in temperature either in kelvins or Celsius is the same. So you don't really need to, convert if you want to find the change in temperature. If they are asking about a particular temperature, then you have to convert. All right. So I hope everybody is clear. If you guys have any questions, do let me know. Okay. Now going forward to the next one, what is meant by Avogadro's constant? By the way, Avogadro's constant is the number of particles per in in 1 mole of substance, right? Or per unit mole. So you can write that as well. So then it says state the relationship between this molar gas constant, Boltzmann constant. Okay, so we can do that. We know that a first equation state I taught you was PV equals to um one moment. PV is equal to NKT, and then I've given you the equation PV is equal to nRT as well. So they want us to find the relationship. So PV equals to PV, which means NKT will be equal to nRT. T and T will cancel out. So NK equals to NR, right? So this is the main thing. Now, what do we need? We don't need basically either small n or n. So n basically is equal to n over na. And Na is, so let's put it in. So here you see Nk equals to, instead of n, I'll write n over Na times R. N and n cancels out. So K equals to R over Na should be our answer. Right? So that's the relationship that we are supposed to find. Then in the next one, it says two samples, X and Y, of ideal gases are both at thermodynamic temperature. Sample X has a volume V and consists of n molecules, each mass m. Sample Y has volume 2V and consists of 2n molecules, each mass of 2m. Understood? Complete the table giving expression in terms of n, m, t, v, the constants in A2 for the quantities indicated. Okay, pretty interesting, huh? What do we need to write? We need to write comments, or we need to just write the quantities? We need to write quantities. Okay. So first of all, I think pressure is equal to nkt. So they're asking about the pressure. Hmm. But we can't use, we have to use only this nm tv. So we have tv. We can't use k. So pressure should be equal to n kt over v. But I don't think they have they haven't stopped us from using complete impression in terms of this and the constants. Okay, we can use the constant. Thank God. I was actually surprised that how can we do this then. Okay, so if you see, sample X is volume V and n number of molecules. Sample Y has, so this is sample X, so it will be n kt over V. And here for Y, the sample is 2n times kt divided by, and it has 2v. So 2 and 2 cancels out, so it will also be nkt over v. Interesting. All right. Now let's check the amount of substance. Now, amount of substance generally can be found out as n over na. And in this one, it has n number. For x, I'm doing x here, I'm doing y here, okay? So n will be n over na. For this one, it's going to be 2n. So n will be 2n over na. So we're going to write 2n over na. Okay, that's going to be a little bit different. Then comes mean square speed of molecules. If you remember mean square speed of the molecule, they're talking about the molecules, not the gas itself. So I'm going to use PV equals to 3 by 2 kT, right? If you remember the formula, I hope you do. So in fact, we're not going to use this. We're going to use kinetic energy equals to the half mc square equals to 3 by 2 kt. This is what we're going to do. So we want mean square speed, which is c square. So I think um, this 2 and this 2 will cancel out and will be 3 kt over m. So this is for x, 3 kt over m. For y, it is going to be c square equals to 3 kt, but this time it has twice the mass, so 2m. So 3 by 2 kT over m. I hope you guys understand that. Then comes the internal energy. For internal energy, it is equal to obviously the same thing. Actually, internal energy is 3 by 2 nkt, because this is internal energy of gas, right? So they haven't said anything else. So please remember this. For this one, for x, I think it's going to be 3 by 2 nkt, but that's fine. But for y, if I use internal energy is equal to 3 by 2 nkt, I have 2n in this and temperature is same. So 2 and 2 cancel out. So this will be 3 nkt. And this wasn't very hard. This was just normal stuff, but interesting. Okay. Let me know if you have any questions, kids. Right. Then in the next part, it says the temperature of X is now varied. Sketch the variation of thermodynamic temperature of root mean square speed of the molecules. RMS speed with the temperature. Interesting. Mm-hmm. We have to check. Half mc square equals to 3 by 2. It is talking about the gas speed of molecules. Okay, that's fine. K2. So that means if I make c square the subject, so it will be 2 and 2 will cancel out. Sorry. So 3 kt over m, like that. All right, just give me 2 3 minutes. I just need to open my break my fast. I'll be back. All right. Okay. All right, kids, I'm back. So now we're going to see what's happening. So we want RMS. RMS means we have to take root of this. So it will be C RMS equals to under root of 3 kt over m. Now the thing is, all these things are constant. The only thing that changes is that it's proportional to under root t. And under root t is a curve which starts from 0, but it will be like something like this, all right? Something like this. Not exactly flat, but it's an under root curve. You just need to remember this. There's no easy way of learning this, actually. Okay, pretty good. All right, so going forward to the next, which is question number 4, and that is what is meant by simple harmonic motion. Again, it's a 2-mark equation definition, and we're going to write in 2 steps. Again, you don't need to write 1 and 2. This is just me writing for you. So we're going to say magnitude of acceleration is directly proportional to magnitude of displacement. And number 2, and the direction of acceleration is always opposite to direction of displacement. So you can basically write this down, check everything. Right. Now, speaking of this, then, we're going to check what's the question about. This is a classic question about V and H, displacement and velocity graph. So it says determine the amplitude. Interesting. So what we're going to do is we are going to check the maximum values. Here, this is one value and the other one is this value. So 3.2, 3.4, 3.6. So this is going to be actually 3.5. This is 9, 9.2, 9.4, 9.6. So this is 9.5. So the total length from actually this point to this point is about 6. And if I divide by 2, so that's going to be 3. So I have to go 3 forward. So that means the amplitude, in fact, the amplitude is just 3. And it lies, the center of this lies somewhere at 6.5, which is 6.2, 6.4, 6.6, somewhere here. So this is actually the center of this. So this is going to be 3.0. Now writing 3.0 is essential because of the significant figures. It should be minimum or one more than that. Anyway, show the angular speed of oscillation. Now this is a classic equation of v times h. So that means we are going to use v equals 2 plus minus omega under root x naught squared minus x squared. Now, in case you forget about this equation, so this equation is also given in the data sheet. So refer to data sheet. All right, that's how you can do this. So we want to find omega speed. We can pick any actually. So let's pick the maximum speed. Obviously, the maximum speed is going to be where the displacement is going to be minimum, and it's going. You can pick any speed if you like. Okay, so this is going to be 6, 7, 8, 9, 10. So yeah, 6, 7, 8, 9, and 9.5. This is in centimeters per second, and that is in centimeters. So all good. 9.5 plus minus omega under root displacement we already found is 3 square minus 0 square because that was the maximum, right? So we're going to do this. 9.5 equals to 3. When the root is removed, it will be omega into 3. So 9.5 divided by 3 gives exactly 3.2 radians per second. So shown. That's how it's going to be. Then it says calculate the period of oscillation. We already know it's 2 pi by t. So for this, we're going to use 3.2 and find out. In the actual exam, please don't leave any questions. Even if you don't understand something from the above part, so you can still use the value that they've given if you're not able to show. That's going to be 1.96, or you can write 2 in that situation. Now it says get the variation of h with time. Okay, that's interesting. What do we do now? So my idea is hmm, we know the displacement, we know the time period, but we need to think if we want to use a sinusoidal curve, we're going to see what happened at time equals to 0. We don't have any value. At time, the block is pulled down and released at time. So it means when it was pulled down, it was completely stretched. That is something that we need to keep in mind. So let's take this side is negative displacement and up is positive. So we're going to start. One moment. It's also in the absolute scale. So we go from 3.5 to 9.5 and 6.5 in the middle. So minimum has to be 3.5. So this is going to be 3.5. Let me check if it's correct. 4, yeah. This is going to be 3.5 and 6.5. So this is 5.5. Wait. Yeah. 5.5 and 6, and this is going to be 6.5. This is going to be 7.5, right? And here we have to go 9.5. So this is going to be 8, 8.5, 9, and 9.5. So this is the value we need. So initially, because it was closed down, so we have to start from this particular point. Okay, then the whole time period is about 2 seconds. So it must come back to 2 after this. And at 1 second should be at exactly 6.5. Oh, wait. You have to think. Hmm. It makes a cosine curve, you know. Hmm. Half of the wave, it has to be at 9.5 actually. So yeah, I think it would go somewhere here like this, and this should cross at 6.5 in the middle. So let's put it here. So like this and like that. That would be one wave. We have to make so many. Then 4 seconds, and then 6. Same goes here. Make sure you plot the right points. So it should look like this actually. All right. One more tough question actually. Interesting. So my kids, that's pretty good. So we done half the paper. And now in the next class, we want to start with the half of it. All right. So now just want to tell you a couple of things. When you go to the classroom, please, you will see 2 files. Okay. One is the past paper booklet that you need to download from this link. And then when you open it up, every day when we do something like on 16 March today, we are doing this paper. So the timeline also given. So you have to complete the paper before you enter into the class. All right. So I will see you then in the next class. Have a nice day. Bye.